Okay, so the last part of this lesson talks about properties of ionic compounds. So in terms of how they behave, what they may look like. So we'll go through that here. So all ionic compounds actually take on the same type of shape. So their shape is what's called a crystal lattice shape. Okay, so first of all ionic compounds are solid at room temperature. Okay, so obviously we can heat them up to make them into a liquid, but at room temperature they are solid. Okay, and you're also going to see this term salt. So when we say salt, really that refers to any ionic compound. So it can be sodium chloride, it could be potassium fluoride, it could be magnesium oxide. As long as if it's a metal non-metal structure, we can technically use that term. Okay, so this crystal lattice shape, the reason why it takes on this form, they almost look like little mini cubes. Remember that when an atom gains electrons, it tends to form a larger structure, right? So when you gain an electron, you're creating more repulsion. So these larger circles are representing the negative ion. So it doesn't matter what it is, right? So if we use an example of magnesium oxide, right? So magnesium is a +2, oxygen's a -2. So these greens would represent like my oxygens. The little ions here, okay, are representing the metals. So remember that when electrons are lost, their ion takes on a smaller size because you have now less electron shielding. So you're losing that outer layer of electrons. So what's holding this together? So you have to imagine if all the green were like negative, all the little blue ones were positive. Right, so what's holding this structure together is the attraction between opposite charges. Positive and negative attract. So that's why the green are kind of surrounded by the little blue positives, and the positive is surrounded by all of the green negatives. So remember, that's called an electrostatic, smells here, electrostatic attraction. So that positive and negative charge is incredibly strong. So this is a very strong attraction. Now, going through some other properties. So structure is always a crystal lattice solid. Now this term SATP, you're going to see this come up time and time again. So that stands for standard ambient temperature and pressure. Essentially, it's a way of representing room temperature and room pressure. So meaning, if we were to just open up a container of an ionic compound at room temperature, it will always be a solid. Melting point and boiling points are generally high. Okay, so the reason why they are high is because, remember, that positive-negative attraction is very strong. So if you want to pull those ions apart by melting it or boiling it, it's going to take a lot of energy for that to happen. Typically, if your melting point and boiling point are low, that means that the attraction is not very high. So like they're easy to pull apart. Electrical conductivity. So what we're referring here to is conducting electricity, right? So they are actually excellent conductors of electricity, but they are not excellent conductors when they are in their solid structure. So they either have to be molten, okay, which means that they are essentially melted down into a liquid form, or they are aqueous. So if you remember seeing this, you've seen this before in grade 10, that means that aqueous means that it is dissolved in water. I was going to say soluble in water, but it means the same thing. So if something is aqueous, that means it is dissolved in water. So all ionic compounds can conduct electricity, but they either have to be liquid or dissolved in water. And the reason why is because you need free-flowing ion charges. When they're in a solid state, they're not free-flowing. So they're kind of just stuck together in that cube structure. And solubility in water essentially is talking about, can we dissolve this in water? Generally, almost all ionic compounds can dissolve in water. There are a few that don't, but a majority do. And as you see here, all of these properties discussed result from that electrostatic attraction. Right? So the more attracted those particles are, the higher the melting and boiling point. Right? When we start looking at covalent structures later on this week, you'll see that there's going to be a difference here because there's going to be different attractions. Okay, and the last part that I want to go through is how do we represent ionic compounds with those Lewis diagrams we mentioned before. So I'm going to do a few examples with you. Okay, so I'm going to do this first one. Then I'm going to have you pause the video to try these on your own, and then we'll take this up. Okay, so the first thing you want to do is start by drawing the Lewis dot diagram for each of the elements. Okay. So here is my calcium with 2 valence electrons. Fluorine has 7 valence electrons, like we mentioned at the beginning of the video. You look at the group on the periodic table. Now, metals will always lose electrons. So what you're going to do is you're going to show with an arrow that the electron from the metal is transferred to the non-metal. Now you'll notice fluorine is now going to be full, but calcium still has 1 more to lose. So anytime that you're doing an ionic compound, you want to keep adding elements until all of the electrons have been stabilized. So meaning because we have 1 more electron to lose, we're going to add in another fluorine. So each of these fluorines are now going to be stable, and this calcium is also going to be stable. So what we just showed here is the formation of the ionic compound. Okay, so the formation. So formation basically means you're showing the electron direction and the number of atoms, right? So I show here that I need 2 fluorine. The next part to this is the final compound. So we always put our elements now in brackets because it is an ion. If it is a metal, you should now show that those electrons have been lost. So see how my calcium, I don't have those 2 electrons anymore, and my charge is positive 2. My fluorine, I have 2 of them. Okay, so the big number 2 in front, the coefficient tells us how many we have. And since I've gained electrons, I have to show that this is completely full. So my fluorine went from having 7 to now I have 8. And each one of those fluorine has a -1 charge. So this structure here that I just did with the brackets is called a final compound. So if you're ever asked to draw the formation and final compound, this is what it is referring to. So formation is with the arrows showing the transfer. The final compound is with the ion brackets indicating the charges. Okay, so pause this video, try out lithium and sulfur, and then potassium and oxygen, and then press play to then see if you were right. Okay, so we're going to do our lithium and sulfur. So lithium has 1 valence electron, sulfur has 6. Lithium is our metal, so it's going to lose. So we need to add in another lithium because sulfur needs to gain in a total of 2 to have its 8. So the final compound here would be lithium, making sure it's empty. There are 2 of them. Each one has a +1 charge. So you have the big number 2. Make sure your bracket is empty, and then you have our +1. Your sulfur should have all 8 electrons drawn in, and it has a -2 charge. Okay, so formation, final compound. Now if we wanted to give this a name, right, so this would be lithium sulfide. Remember, the metal does not change. Lithium sulfide. And the formula, of course, would be Li2S. So this is our formation, final compound. Lithium sulfide would be the name, and Li2S would be the formula. Okay, so then our potassium and oxygen actually work similar. So you have 6 valence electrons on oxygen. Ooh, too many. Too many. So we have 6 valence electrons on oxygen. Our potassium has 1, so we would need 2 potassiums. So again, it's very similar actually. Potassium, ooh, oh my gosh, my brackets are out of control here. Positive 1, and then my oxygen would be full with 8, and then the charge is negative 2. So this would be potassium oxide, and then the formula, I'm not going to write it out, but potassium oxide, and then this would be K2O. Okay. Now for homework, you're doing a worksheet to practice all of this. Just keep in mind the name. So this is our formation, final compound. Name would be potassium oxide, and then the formula is K2O.